Okay, we begin the afternoon session with the first talk by Manohar Kumar, that's the correct pronunciation, on a title which is written here.
Thanks, Yuval. I would like to thank the organizers to Thank you, organizer, for inviting me to such a wonderful gathering. And since last 5 days, I have to say that I'm enjoying the wonderful weather of Bangalore, wonderful food, and the good science. With this, in this session, I would like to talk about Josephson relation, fractional charge, and Abelian statistics for anion. So I think so far you guys have already known what anions are. You have a talk from Eduardo, and Gopinath is also there. So basically, you guys know the fractional states. Fractional states, is it audible now? Okay. The fractional states are not the electronic excitations, but they belongs to a different class of the group called anions. And this talk is all about the fractional quantum Hall states and how we are going to really characterize them. So when you talk about the anions, as you have seen in Eduardo's talk or lectures, these anions has two characteristics. One is basically the charge, which you characterize by measuring the noise. And the second is the statistics. So unless until you do both of these experiments and classify that, you can't say that these particles belongs to anionic group or not. So I know that Gwendal was here in the last week, and he already presented our results on anionic braiding statistics. So I will not go into detail of that, but just to give you a summary who missed his talk. So what we did in our work is basically we created one quasi-particle on fractional H and another quasi-particle here, and then we collide them. So the quasi-particles which we create here, they have the anionic statistics, and when they go to the QPC, they usually braid. And by braiding, you see the signature in cross-correlation measurements. But if you want to know more, probably you should see the YouTube video of his talk, which thanks to ICTS, they posted those videos online. Now the scattering noise measurements is basically, everyone knows it. I mean, it's starting in 90s, done by the two groups. One is Weizmann group and other is France. They have studied the fractional states by the scattering noise. It's well understood. So basically they really can say that what is the charge of this quasi-particle in these fractional states. And by the way, these anionic statistics and this fractional states quasi-particle charge measurement both are measured at the DC. And DC means literally they are not putting any AC currents on those systems. However, you could do more if you try to probe them with the microwaves. So now in this talk, I'm going to going to give you the glimpse of what you could do when you try to probe them with the microwaves. So let's start with a brief introduction to the noise. So if you have a quantum conductor and you apply a bias voltage, so basically you have two quantum conductors separated by a tunnel barrier, and there's a difference in the chemical potential EV, then the quasi-particle or the electron will tunnel through the tunnel barrier. And there is a probability of tunneling. So there is no there can't be a deterministic process which allows you to the electron to tunnel from here to here. So there would be a finite probability. So some electron can go and some electron can reflect back. This probability of traveling of electron from the left to right give you some kind of a noise. And that's what you see in this kind of system. Here you're seeing a bow tie sample where you have a edge states going in this direction, edge states going in this direction. Using a QPC, you try to bring this quantum Hall edge states closer to each other, and then there is a certain probability that top edge will scatter back to the lower edge, and that will create the noise in your system. And if you measure the noise, then basically this y-axis is the noise, x-axis is the voltage, you will see something like that. If you try to fit the data, then basically the noise is proportional to 2q I naught t into 1 minus t. The Q is the charge of the quasi-particle, I naught is the total current which you're putting into the edge, T is the transmission probability, 1 minus T is a reflection. And that's it. So now you see that by measuring the noise, you could measure the charge. And that's people has done it, not only in fractional quantum Hall states, but also in the condo systems and superconducting junction. So it's okay, you could do that, but the story is not so simple. Quasi-particles, you can't always measure the quasi-particle charge because the noise, somehow in the short noise, when you try to do the DC, the fractional charge and the scattering properties of conductors are mixed. They can vary with the temperatures, they can vary with the transmission probability. And there are a list of the papers. I'm just listing a few. This is a recent one, probably you should try to interact with Yuval also, he is here. Even in superconducting junctions, you should see a 2e charge when you try to tunnel the quasi-particles of superconductors. But however, when you change the tunneling probability, you see the quasi-particle charge changes from the 2e. So really the short noise doesn't give you the full picture of your quasi-particles when you're measuring at the low frequency. So that's why we try to find a new system where we could really find the charge of the particles independent of the properties of the system. So really probe the dynamics of the charge, not related to the conductor itself. So we thought of, let's try to do the high frequency noise measurements. And the motivation is coming from the lots of other earlier experiments. So basically, let's start with what the high frequency means. So let's say that you have two quantum dots as you're seeing this in picture. And if your source and drain align with the energy states of the quantum dots, if electrons tunnel from the one quantum dot to next one, it will emit the photon. Now the question is, what will happen instead of a quantum dots if you use the Fermi sea? So if you have two Fermi seas separated by a tunnel barrier, in this case, if the electron tunnels from here to here, what will happen? You will emit the photons. But there's one difference between this and this. In this case, the electrons which are residing here, it can also tunnel and it will give you the photon energy, but the frequency would be lower. But in this case, you will only see a one photons coming because of the discrete energy steps here. So you have multiple photons emission in this case, but maximum frequency is defined by what is the voltage difference between left and right Fermi sea. However, you can't put any, you will not get any photons higher than the frequency defined by EV is equal to h nu, simple because the electrons which will have a higher energy will not go inside the Fermi sea, and that's defined by the Pauli exclusion principle. So that's the potential difference between left and right defines what is the maximum frequency you are going to emit, okay? So now let's try to see, is there any similarities between, which I think all of you guys know about the superconductor. So if you take two superconductor and separate by a tunnel barrier and you bias them with the DC voltage, then you generate an AC current. And this AC current will have a frequency which is 2 EV over H. That's we call it Josephson frequency. So there are the similarities between the microwave emission in the normal metal conductors and this Josephson frequency in case of the superconductor. So that's why most of the time when you hear the talk or you will read the paper, people call this as Josephson frequency. Okay, so let's again start with the zero frequency noise. If you try to measure zero frequency noise, you will see the graph like that. So if you go to the higher bias voltage, since you have more and more electron tunneling through the system, so the more a scattering process, the noise will increase linearly, right? But now the question is, what will happen when we try to measure with high frequency noise? So let's think of one Gedank experiment. What you could do is you have a detector here, which only detects at the frequency F. And then you have two Fermi seas separated by a tunnel barrier. In this case, what you will see. So if you put the bias voltage something like that, it will emit the photons which have a lower energy than the frequency which your detector can detect. So basically you will not see at all anything. If you go, so basically you will be somewhere here. And if you increase the bias voltage above the frequency which is your detector can detect, then there's always a finite probability that some of the process will emit the frequency which is corresponding to your detector frequency. And then you will see some noise. So basically you will be somewhere here. So that's why you will see some kind of a threshold in your measurement if you do the high frequency measurement. So contrary to the low frequency noise measurement where there's no threshold at all, in this case you will see a threshold, and this threshold is purely defined by the detector frequency, okay? So now let's set up the experiments. If you want to do the experiments in gigahertz, and why we want to do in gigahertz, simply because if you say 7 gigahertz corresponds to 300 millikelvin. And 7 gigahertz, if you convert into the voltage, it's corresponds to 30 microvolts. So most of the fractional quantum Hall states, noise measurements are done in few hundreds of microvolts. And that's why we try to do the experiments in the gigahertz regime. Okay, so let's try to review some of the earlier experiments which people had done in this microwave. So there is one example is gold diffusive wires. Another is the tunnel junctions. Both of these ones has impedance of 50 ohms. So as you know, most of the cases, the high frequency components are 50 ohms. So they could easily couple to it, and then the signals are much larger. So it's easier to measure. And the simple scheme which people try to do is you have a sample here, then you have cryogenic amplifier, and then you have these diodes, which measures the down converted signal. So basically, whatever frequency you are trying to detect, you multiply by the mixture here, and you down converts the signal to the DC, and then you just measure the DC signal output here. So it's very easy to measure, but life is not so easy. Sometimes your sample has a higher impedance, for instance, the 10 kilo ohms. So if you have 10 kilo ohms, most of the signals you will reflect because you are trying to couple high impedance sample to the 50 ohm samples. So the reflection in this case is given by the impedance of your sample minus 50 ohm divided by impedance of the sample plus 50 ohms. So you will see that if impedance is very large, then most of the signals are just reflected. 99% of your signals are just reflected back. So very weak coupling of your sample is there if you're working in order of 10 kilo ohms. So that's the limitation of your measurements. So basically, high frequency amplifier have a noise of 4.2 Kelvin, a signal is an order of 10 microkelvins. So that's limitation or challenge which people face when you try to do this kind of measurements. However, people are doing the experiments. So what you see here is the noise in terms of the temperature. And this is the bias voltage. There are two sets of the data, red and blue. The red curves has higher frequencies. So red curve is measured at 7.63 gigahertz, and the blue one is measured at 4.22 gigahertz. So what you see here is higher the frequency, higher the threshold would be, simply because you need to go to the higher bias voltage to go over that. Okay, and by the way, this measurement was done at the 0 Tesla. So this is again the 2-day, no magnetic field was applied, so it's a 0 Tesla. So it's a pure Fermi separated by a tunnel barrier defined by this QPC here. Now, let's ask ourselves, this is true for the Fermi C, but what happens if you try to replace this with the Laughlin liquid? Can we see a similar kind of a physics there? So the questions are, will the microwaves, which is emitted by this, will carry the imprints of the fractional charge? Will there be exclusion principles holding up, or it will be invalid? I think you have a question.
Well, yeah. When you write Laughlin liquid, different chemical potentials, you still mean the same filling fraction.
Same filling fraction, yep. So let's presume that if there would be a threshold, then we will see a feature like this, and that's what we should look. So let's start with experiments. So this is our experimental setup. So what we have it here is a bow tie sample with a central QPC here, and they have a 4 ohmics. At ohmic 4, you have a high frequency line. I will not describe it right now. I will come back later. But at the ohmic 1, you give the DC voltage, which gives the potential to an edge. And then you measure the noise at the ohmic contact 2, and ohmic contact 3 is grounded. These are detail of the samples. I will not go into detail of those. So let's try to do the DC noise measurement. So if you take the nu is equal to 3 states, the third plateau is up in the graph, which I'm not showing it to you, but you have 3 plateaus. And if you try to measure noise at the plateau, you will see a 0 noise. That's ideal. Ideally, you should see. I think Yuval might be differ on this. But in some of the cases, you see the noise, which Yuval comments on it. But now let's imagine the case, if you put your QPC such that you are partitioning the edge states 50-50. So 50-50 means you have 50% probability that the electron will go from left to right, and 50% get reflected, but this process purely random. That means you have a maximum noise. So we put ourselves somewhere at the 50-50 splitting case, and then we measure the noise. If you measure the noise, again, this is y-axis excess noise. Excess noise simply means I subtract the thermal noise. So if you're measuring any noise in your system, there's inherent thermal noise because of the finite temperature. So if you subtract that, then you will get the pure short noise. So this is excess short noise, and this is a bias voltage, and you see pure, this data scales up linearly, that's what we expect. And if you try to put the formula fits here, and then the fitting, we just use the voltage, which we know what the voltage we are applying. We know what is the electron temperature of my system is. We know what is a G naught, which is a conductance. So we could find the Q, where the D and 1 minus D is the transmission probability and reflection of this QPC here. So you could see the experimental data is beautifully explained by this simple Landau-Buteyko formalism. Now let's do with the fractional quantum Hall states. So now we are taking nu is equal to 4/3. So nu is equal to 4/3 simply means you have two edge states, one carrying a electronic excitation nu is equal to 1 plus 1/3, which carrying the electronic excitation of 1/3 charge. We put ourselves at the weak backscattering limit. That means most of the excitation will be able to travel through the QPC, only partly get reflected back. So that's why you see we are putting ourselves somewhere here and then trying to measure the noise. When we do the noise, again, you see we could explain this data simply by putting this formula there, and you could identify what the charge is taking place in scattering process here. We go and try to measure the 2/3. In case of 2/3, you will have two edge channels. One is 1/3 here, another is 1/3 here. Each of them carrying a charge of 1/3. And then if you try to measure the weak backscattering limit of this point, you see the noise easily explained was the electronic excitations, quasi-particle excitations taking place in this scattering process. So with the let me summarize. So if you do the low noise measurements, you could identify the charge, right? Now we have to do the high frequency noise measurement. That's I promised to show you. So before that, the technical challenge that I already explained to you, if you try to work it out with this formula, the signal which you are trying to measure is a 50 microkelvin. The best amplifier in the market, which you try to buy, you get the noise temperature of 3 Kelvin. So it's almost like you're taking an ice cube and going toward the surface of the sun, and you're hoping that your ice cube will not melt. That's the basically challenge of experiment, what we are looking for. It's just a pictorial representation, but that's explained more challenging than what we are doing it here. So don't take it literal way. So this is high frequency noise measurement, which we are trying to do. So what you see here is basically the sample is connected via this coaxial line, then this is a hybrid coupler. And there's a parallel chain of the amplifiers, there's a second hybrid coupler. So these two combines forms a Mach-Zehnder interferometer. So what you do here is basically you take a signal, you split the signal into two arms of the amplifier, and then using a delay line here, you could tune the phase and push the signal of this line, which is your sample signal, will go in this line. However, this line will contain the amplifier noise, and this line will also contain the amplifier noise. Now using a differential modes, you could add and subtract them to somehow just to get the noise of your signal. So that's how it looks, sorry. So what you see here is ideally in case your sample signal would have a sum of your amplifier noise, equilibrium noise, and on the top you have the signal noise there. If you do that, then you will get only the signal noise coming out of your sample. On the top, I mean, this way you could get rid of the amplifier noise. What to do with the noise which your sample already has it because of the finite temperature? If there's a fluctuation in temperature, because your omics will see the fluctuation in temperature, that will corrupt your signal. In order to get rid of that, we modulate the voltage on my signal here. So let's say if I need to apply a 1 volt, then I will measure the noise at the 1 volt and 0, and then subtract the noise at 0 volt from the 1 volt. By doing so, we cancel all the thermal fluctuations which is happening because of the omics, seeing the temperature fluctuation there. So in this way, we get a very clean signal out of it, and we get the noise sensitivity to the order of 5 microkelvin. That's what we required. Okay, so with this, let's start with the high frequency noise measurement. So again, we try to put in the 50-50 beam splitter case, and we try to measure the noise. As we have seen in earlier case, we are also seeing some kind of thresholds, and the way we identify this threshold is we put the linear fit of this data and then the flat lines here. And by the way, this is axis high frequency noise. So the crossover gives me some kind of a threshold voltage. We could also fit this data just using a weighted average of the Lezovic-Levitov formula, and that it also fits very nicely with the dashed dot lines here. We go and do with the fractional states. Okay, I think somehow it's not working. But anyway, so this is the case for the fermionic case. Okay, now it's good. So this is case with the fractional states when I'm trying to do the scattering noise measurement in high frequency regime for 4/3. And what you see here is some kind of a threshold. And this threshold, again, we identify is 80 microvolts. And let's try to compare the fermionic case with the fractional states case. So this is a fermionic case, and this is a fractional state case. note that the frequency for this measurement 6.6 gigahertz and frequency for this measurement 7.5 gigahertz. So as I told you in earlier case, the higher the frequency, the higher the threshold would be. But in this case, what you see here is the threshold is smaller, although the frequency measurement is higher. So that simply means there's something more going on. And if you really fit this formula, you will see the charge here it corresponds to 1/3, and charge here is 1. Even if you just look into the threshold voltage, which we can EV is equal to h nu, from there we could identify the charge. And that's just to give you confidence. This one is, if you try to measure the same frequency, this is expected noise if you measure the high frequency. If you measure at the frequency required for this one, with the charge, it will be something like this. So clearly shows that it's not the arbitrary, it's really intrinsic to the sample and the charged particle which is taking part in this measurement. So with this, we could easily identify what is the charge of this quasi-particle is taking place at the scattering points. Now what I'm trying to do here is I'm trying to scale up all the data. I'm scaling the characteristic frequency here, and I'm also scaling with the characteristic frequency here. So basically all the data are collapsing on the top of each other, and they clearly show us some kind of threshold. So by the way, it contains the 3 different measurements, nu is equal to 3, which should contain a charge of 1, nu is equal to 4/3, which contains the charge of 1/3, and nu is equal to 2/3 contains the charge of 1/3. And all of them scales up if you scale them by the charge, corresponding charge. That's a beautiful representation of how the high frequency noise look like and how they identify the charge in the systems. Here I'm plotting a threshold voltage, and here I'm plotting the gigahertz frequency at which I'm trying to measure my signal. So red ones are corresponding to the quantum Hall states nu is equal to 3, and these are the fractional states which should carry a charge of 1/3. And by the way, the dashed lines, these are expected value for threshold voltage for corresponding frequencies if you try to measure charge 1/3. So this is not the linear fit, by the way. And you see this linear line clearly within the error bar of my experimental data shows that the charge carrying by the fractional excitation and high frequency noise really shows the charge of 1/3. This is a simultaneous experiments which came out from the collaborating group in Saclay. So what they did is instead of measuring the high frequency noise, what they did is basically they signed the samples with high frequency microwaves and try to look at the DC noise. So these 2 experiments are complementary. And what you see here is again this straight line, which is showing the expected value of a charge of 1/5 if you try to measure the charge of filling factor 2.5. And these are the experimental data. Again, this shows a clear demonstration how the high frequency noise could help you in measuring the charge there. We went one step ahead and tried to understand that how this finite frequency noise will look like if you try to use the fluctuation dissipation theorem there. So this is the fit which we are trying to do in our measurement. But then Ines Safi, which is a part of our work here, so she tried to look into fluctuation dissipation theorem and try to identify what is the finite frequency noise. And in case of the finite frequency noise, this would be the formula. And you see that this is simply this one, but on the top there is some nonlinear element which is coming up here, which is just because of the nonlinearity because of the backscattering current. So usually the QPC induces the nonlinearity in the system, so there is some kind of deviation from this formula. And if you include that, we could easily fit our data very nicely. So this one fits much nicer compared to this Lezovic-Levitov formula there. So with the 3 mechanism, we could identify the charge in high frequency noise, but the most interesting part is basically this just threshold voltage, which is independent of your amplifier gain, non-electronic temperatures, and so on. So you could easily identify what is a charge. So it's much better way of measuring a charge in fractional quantum Hall states. With this, I think my time is running up. I will summarize that you could get the threshold, and from threshold you could identify the charge. But now the question is, how could you measure the statistics? And what happens if you try to identify the Laughlin and composite fermionic states? These are the 2 different. Classic example is 2/5 and 1/5. So these are the experiments which is ongoing, and hopefully next time we would be able to answer this. And this was the team which works. So basically the samples came from this group, and the theory was done by Ines, and the experiments were done in the LPNS. And now I moved to Alto. So this is how it looks when I was flying to India. And this is my small group. And we are working on electron optics in the graphene and the TMD. So next time, maybe I'll be presenting more on this side. Thank you.
Thank you very much.